Well, good afternoon to you. Welcome to the real rump session of the Entropy Group. My name is Simon Ricks. I'm the lab manager at EWA Canada for FIPS, and it's my privilege to greet you this afternoon. Our first speaker, I think, needs no introduction. Joshua Hill, KeyPair, mathematician of note, stirs the water in most of the Entropy working groups. Josh is here to talk about his latest thinking on health tests. So Josh, take it away.
All right, well, I'm not sure exactly how much a mathematician of note I am precisely, but in any case, so what we're going to talk about today is the APT and RCT, and in particular, and this is a little discussed aspect of this, selection of their cutoffs. And by that, I don't mean, hey, what does 90B have to say about that? I'm really interested in exploring sort of what the consequences of using the procedure described by 90B is, and to provide a few alternatives that I think are also viewed as broadly acceptable by NIST. So let's wander into it. So the 90B cutoff procedures yield APT and RCT cutoffs that have low statistical power for most noise source designs. And by that we mean they don't necessarily do a very good job of detecting particular failure modes for actual implemented entropy sources. And designers actually, as it turns out, are allowed to choose cutoffs that yield a more powerful APT and RCT, which, as it turns out, also have false positive rates that are actually much closer to their targeted false positive rates. So, you know, as is standard, it turns out that when you start messing with these cutoffs, you're going to ultimately affect what your false positive rate is. But in this particular instance, you're really just making your false positive rate a little bit closer to what you're targeting. And in addition, the APT window size can be tailored for the noise source distribution, and that's explicitly allowed in this scheme. So you should definitely think about doing that, and I'll show you some examples where that can make a difference. And then also, if you're interested in figuring out what cutoffs are appropriate, there are software tools to help you to do that empirically. And we have a set of them, and they're publicly available. You can download them and use them for free. So I certainly encourage you to take a look. All right, so just a little bit of introduction. So statistical tests are generally analyzed using their false positive rate. And it's done that way for a fairly straightforward reason. So the false positive rate is the probability that the test incorrectly detects a failure when the entropy source is actually working correctly. But unfortunately, from a security perspective, that isn't so much relevant. That's more interesting from a usability perspective. You know, you care when things say they failed when really they haven't. But from a security perspective, you're more interested in something called the statistical power, which is the probability that the test correctly fails when there actually is a failure. But as it turns out, that probability, the statistical power, is dependent entirely upon what particular failure mode you're in. And so as a consequence, though there's only one false positive rate, one alpha, there's in some sense a whole bunch of possible statistical powers depending upon what type of failure mode you're in at the moment. So commonly, but most certainly not always, increasing the false positive rate, alpha, it results in an increase in the statistical power. Now, unfortunately, it isn't always, because sometimes these tests sometimes turns out that the noise source fails in a way that the test is particularly not very sensitive to, and so you can get these things that are most definitely clearly failures, but don't trigger really either test, no matter how high you push the false positive rate, essentially. Okay, so some important things to recognize about the APT and RCT. They are categorical, so data encoding is completely irrelevant. Doesn't really matter how wide your data is, doesn't really matter how you encode it, as long as you can test for equality, since that's really the only thing they care about. As long as you can tell when two symbols are equal, which I guess I can't think of too many situations where that's not possible. As long as you can tell, then you can do these tests. So for many noise source distributions, the parameter that actually establishes the false positive rate is the probability of the most likely symbol. Now, this may sound familiar to you because, in fact, the probability of the most likely symbol sort of plays into the sort of straightforward definition of min entropy. And in particular, if you've got a stationary IID noise source, then as it turns out, that is precisely what your min entropy is. The sad truth of it is, though, the first part, if you had a stationary IID noise source, that essentially never happens. So the answer is you don't have a stationary IID noise source with high probability. And so instead, what you're left with is, okay, well, so then what happens? And the answer is, when you look at your data empirically, or when you model your system or use a stochastic model and establish, hey, what's the most probable symbol, that will play in very specifically into, it surely provides an upper bound for min entropy. That's not that interesting. But more to the point, it provides you a good indication as to how the APT and RCT are going to behave, and it gives you a good way of modeling false positive rates. So first, just as a quick reminder, I'm not going to spend a lot of time on this. I'm sort of assuming that if you're here, you already have looked at the 90B standard and have some vague notion as to what the APT and RCT are. So this is going to be a running introduction to these. APT, basically, you have a window, you count how many times a symbol occurs within that window, and then if that count happens to go above your cutoff, then you trigger a failure. Quite straightforward. The window size is a configurable value, however. So the window size is specified in SP 890B are 512 for symbols that are multi-bit, that have more than 2 symbols in their alphabet, and it's 1024 for binary systems, where you only have 2 symbols that you produce. Okay. So the whole point of the APT is it's intended to eventually detect the most likely symbol becoming dramatically more common than expected. Turns out that this happens even in situations where your noise source is not a stationary IID system. You still have some advantage to using the APT in a lot of situations. Sort of a classical example, just for a quick example here, is if you have a series of ring oscillators, you're sampling them and then concatenating their outputs into a multi-bit symbol. So if you have 8 ring oscillators and you produce a byte at a time, that means that if a ring oscillator fails, its output becomes stuck. That means that if 2 ring oscillators become output entrained, then the relationship between those 2 bits are necessarily fixed, and that reduces the total available symbol space in that failure mode, and as a result makes it so that the APT has a very good chance of detecting it, assuming you set up the cutoffs appropriately. So this is something that can be useful in a lot of different settings. And more to the point, if conversely you have a failure mode that doesn't affect the probability of the most likely symbol, then that isn't a sort of failure mode that's likely to be detected by this particular health test. No? Okay, well, I guess I'll use the keyboard. No? I say something grabbed focus. Very convenient. Okay, so APT cutoffs. The particular APT cutoffs that are actually described in section SP 890B, section 4.4.2, it turns out there's some minor statistical corrections there. It doesn't have a major impact on the cutoff, and frankly doesn't matter too much. It's off by 1 sort of thing. But more to the point, these are cutoffs that are developed under the assumption that you have a IID stationary noise source. So a noise source that produces IID and stationary, has an IID and stationary distribution. And it, as a consequence of that, bounds the false positive rate using the assumption that the APT reference symbol, which is the first symbol it encounters in that window, is in fact the most likely symbol. So those are 2 assumptions, one of which is essentially almost never correct. That is to say, most actual functional noise sources aren't IID and aren't directly stationary in the sense that they produce the exact same probability for the symbol over a very long period of time. And then secondarily, this secondary assumption where you're saying, well, I guess the first symbol I've encountered is, I guess, maybe the most probable symbol. Well, sometimes it is and sometimes it isn't. So if you want to estimate what the actual false positive rate is, the most straightforward way of doing that is probably just doing large-scale simulation. Okay, so as I mentioned, most noise sources aren't IID or stationary, so if the APT is cut off under that particular assumption, then the targeted false positive rate generally isn't attained. In fact, it's oftentimes dramatically different. Generally, in fact, almost always, it is the actual false positive rate is dramatically smaller than the targeted false positive rate. And as it turns out, if you happen to generate cutoffs using the NIST procedure, it turns out that if you're using very large cutoffs that are very near the window size, which are associated with very high entropy assessments, or very small cutoffs, which are very near zero and associated with very low entropy assessments, those are likely to result in lower than desired statistical power even on systems that are stationary and IID. So just as an additional aside, if you're reducing the symbol space prior to testing, like mapping the symbols down, that tends to make the APT worse in the sense that both you get a corresponding higher false positive rate and you get a corresponding lower statistical power as a result. So it tends not to be terribly helpful. Okay, and then next, let's talk about the APT window. So the APT window is the number of the chunk of symbols that you actually are within there, counting the number of times that the reference symbol is present. So as I mentioned earlier in the presentation, that's expected to be 512 or 1024, depending upon what the system is, 490B as written. However, it's really important to note that actually NIST allows you to choose other values so long as you actually justify why you've chosen that other value and what benefit you get from it. And it's important to note that doing so is basically fairly painless. I've actually never had any pushback, even after just saying here's a couple lines as to why a different window size is appropriate, and it's basically been fine. At the same time, you don't want to abuse that and say, well, my 2-symbol window is obviously the way to go because it's fast, so fast. Because fundamentally that also makes it so the test is completely non-functional, so that's sad. So you actually want to have some notion as to how you're tracking the statistical power and in particular how that relates and how that compares to the default settings, essentially. Okay, so reasonable choices, even for wide symbols, would include things like 1024 symbols, 2048 symbols, or even 4096 symbols. And you can get some actually fairly impressive false positive results with these larger window sizes. You don't want to let this window grow without bound. Eventually you do genuinely run into real problems where you just have very few opportunities to fail. So the particular place to kind of consult as to whether things are working or not is probably 90B section 4.5. They give you a very specific rationale that you may or may not be specifically required to make, but at least you can have an eye toward that and say, given 50,000 symbols, what is my chance of failure? And it would be nice to be able to make a statement about that. Okay. So if we want to explore how window size really impacts this, let's go ahead and look at the APT window size in sort of a best case view. It's important, this is a little bit of a weird shift. All the rest of the presentation I'm saying, hey, it's almost certainly the case that your noise source is not IID and is not stationary, but now, by the way, for our example, IID and stationary, because we're trying to show the APT and in some sense its best light. This is the situation that was really designed to test. And so if we're trying to understand how the window size affects it, it makes a lot of sense to at least look at the situation that was really designed to test. So in this example, I'm producing 16-bit symbols with the specified entropy. The cutoff for each test is established using the procedure in 442, and we'll establish the statistical power while we're in the 4.5 criteria B half entropy mode. That is to say, if my noise source produces half of the expected entropy, and given this is an IID stationary system, it's easy to say what that means. That just means a symbol becomes quite probable. What is the chance of that being detected? And so what we can do is we can graph that out. So here we have, many, many thousands of examples. And so here what we see is, I could really spend literally the rest of this talk doing absolutely nothing but gazing lovingly at this diagram and describing all of its various characteristics. And oh my goodness, you notice the little shingles there? Those sort of have to do with, the particular cutoff is being generated using this procedure. And so, look at that, when the cutoff increases, you get some overlap there, isn't that fun, et cetera. We could go on for a long, long time. But what I just want to emphasize here, instead of going on for a long, long time about this exact thing, is we looked at 2 different window sizes. We looked at a 512 window size and we looked at 1024. In this particular case, 90B would have us just, as written, choose 512 because this is a 16-bit symbol. It's quite wide. So in this case, what you should note is that the 1024 symbol window is actually dramatically better. It It actually detects failures quite a bit lower. So even if your entropy is quite low, when you have the entropy, it's still likely to detect it. And then if your entropy is very, very high, same thing happens. So in general, the higher window size, unsurprisingly, this should be essentially a surprise to essentially no one, higher window sizes make the test considerably better in this context. Now, whether that is a better that means anything to you is entirely dependent upon what your actual entropy assessment is. So the entropy assessment here goes over quite a broad range. In practice, probably more folks happen to be looking in this sort of range than are looking in the like full 16 bits of entropy per 16-bit symbol range, but it gives you an idea that it has interesting impacts on both sides. It's also interesting to note that fundamentally there's not a huge difference in that big middle. So if you're in the big middle where the particular window size of 512 and 1024 are basically pretty interchangeable, then it sort of gives you a good indication that maybe choosing the smaller window size is better in that context. Because as we've said, with a smaller window size, you have essentially a little bit more agility in the sense of you're not stuck on whatever the first symbol was, and so you have a better chance of actually genuinely hitting upon the most probable symbol throughout the testing process. Okay, so I'm not sure if you were expecting to come here just so I could deride the hopelessness of using the APT and RCT, but that's not what I'm here to do. What I am here to do is tell you the APT and RCT are actually, they do exactly what they say they're going to do, but what they are going to do is maybe not exactly what you need. And so the APT, what it does exactly what it says on the tin. That's what it does. If your concern is maybe some particular symbol is going to become more probable, and maybe that's because some ring oscillators failed, and so some of those things become fixed with respect to each other when they become trained. I mean, those are all things that this will pick up on, even though that's not precisely what it was designed for, but it turns out that it has the effect of actually failing in those situations, and so long as you choose a reasonable cutoff, you'll detect such failures. On the other hand, there are some systems for which the APT, as basically specified, is essentially unuseful in detecting failures. So classic example of this is any system with feedback. If you have a binary system with feedback, one standard failure mode in that case is literally alternating back and forth 1, 0, 1, 0, 1, 0 for the entirety. And so if you're doing a 1-bit APT, your chances of detecting that in the APT is 0, because that looks great every time. And similarly, the chance of that failing a RCT is 0. But so this is one of those cases where it's important to kind of recognize what are my failure modes and how am I going to create health tests that actually test for that. As DJ was quick to point out, it turns out you can take the APT and do some fun stuff with it. You can take it and form larger symbols, and suddenly the APT becomes helpful. So that's an interesting point. Okay. So next, wandering off to the RCT. So the RCT, and again, I'm not going to dwell on this. I'm assuming you're pretty comfortable with this already. Essentially what we've got is we read something and then we check to see if it's equal to the next symbol. Wash, rinse, repeat. So if you read through this, that's essentially what it says. You're looking for runs of a particular symbol. So in some sense, this is what the AAS 31 would refer to as a total failure test. So this detects, this is the nice part about this particular test, is that this is a strikingly common failure mode. You have a piece of hardware, if it just starts outputting the same exact bit every single time, that's something you'd like to actually detect fairly quickly, and this test will do that for you. And there's all sorts of failures that can cause that. Basically, if you imagine you've got, hey, this chunk of hardware, we're basically sampling something, if one of your output gates dies, then suddenly it's going to be outputting that same value over and over again. And that's the sort of thing this easily detects. This is not necessarily a failure that happens all the time. It's not the most subtle of failures. It's definitely a failure that happens, though, and it's a useful test as a result. Okay, but if you look in the opposite way, if you are looking at a failure mode that doesn't tend to result in long runs, then this is not going to detect that for you. Okay, the cutoffs here essentially make the same assumptions as the APT, so I'm not going to talk a lot about that. So the actual false positive rate is failure mode specific, and the failure mode associated with a particular RCT cutoff is distribution dependent. And so you end up ideally trying to estimate that using some sort of large scale simulation ideally is probably the easiest way of doing that. Though as it turns out, this particular test, if you've got a stochastic model, actually it's pretty easy to come up with nice close form solutions as to how you think it works from a, for certain types of failure modes. Okay. So again, just like the APT, most noise sources aren't stationary or IID, and so if the RCT cutoff is established using the assessed entropy, then the targeted false positive rate isn't likely attained using this procedure. This is another case where if you go through the procedure in 90B, targeting a particular false positive rate, and then actually take a whole bunch of data and shove it through the test, you'll find that the number of failures you actually experience is dramatically lower than the number you sort of anticipate experiencing, even when it's, even though the test is working fine, even though the source itself is working fine. The answer is just your notion of what the false positive is, as it turns out, not quite right. Okay. So the RCT similarly does precisely what it says in the tin. If what you're concerned about is fixed values or long runs of a particular symbol, this is an excellent test for detecting that. If your failure mode doesn't cause those things, then this isn't going to be a very useful health test for you. So, and as it turns out, I mentioned earlier that oftentimes what essentially dictates the behavior of these things is something that I was referring to as apparent entropy, where apparent entropy is established entirely by the probability of the most likely symbol. And so if you're attempting to assess what particular cutoff you're to use, one approach is to say, well, what is my apparent entropy, either from very empirically by a very large number of very large sample, attempt to estimate it that way, or using a stochastic model or some sort of other model that gives you some insight as to what sort of data is output. And in those situations, you can actually come up with somewhat nicer cutoffs that give you better properties, both from a failure mode and in a sort of statistical power within those failure modes, and with respect to actually getting closer to attaining your false positive rate. Okay, so I keep on saying, hey, there are other ways of possibly choosing these cutoffs distinct from what happens in 90B. And so what I want to do is sort of talk through some possibilities. So one possibility is if you're choosing one of these estimates, other than based upon the assessed entropy H, then what you really need to do is explain why that's happening. And so NIST allows for adjustment of H for the purpose of health testing, and so but one needs to talk about why one has done that. And so one possible way of proceeding forward with this, as I mentioned, was to go through and come up with some notion as to what you think the H apparent is, and essentially base your cutoffs on that. Another possibility is to use some sort of empirical system where you actually take a very large amount of data, either real or simulated, and shove it into these tests and actually come up with a cutoff that way. And for, as long as your false positive rate, your desired false positive rate is not too small, that's quite practical. If your targeted false positive rate, for example, is 2 to the negative 20, that means that you're really only looking at a few million samples that you need in order to be able to reasonably estimate what these values are. This becomes a little harder, as we'll see with the APT test, but we'll get that in a bit. Okay, now the end result is that when you use these alternate approaches, that the particular cutoff you choose is almost necessarily considerably lower than the one that's suggested using the 90B procedure. So what that means is you can easily argue that any failure that the 90B procedure cutoffs would find, this would also find, as a result of the fact that it's a lower cutoff. It's just you can quite clearly show that the failure conditions are essentially a strict superset when you choose a lower cutoff. You can also describe, so that is a productive way of argument and has worked in the past, but even if you were uncomfortable with that approach, you could also just say, okay, fine, I'm using a different way of generating cutoffs. These are nominally, or at least conceptually different, even if they're very closely related to the 90B tests, the approved tests. So what I'm going to instead do is I'm going to consider this to be a developer-defined health test. And so it's the exact same health test, but I'm developing the cutoffs in a slightly different procedure. And as it turns out, at that point, you just need to go through and answer the 90B section 4.5 requirements, which is completely trivial if you, in fact, have lower cutoffs. I mean, it's really extremely straightforward. And so as a consequence, you can easily get compliance in a straightforward way that way as well. Okay, so as I mentioned, there are some data requirements if you're going to empirically estimate what an appropriate cutoff is for desired false positive rate. It turns out that the Theseus package has tools called APT and RCT, which you can use to establish cutoffs quite readily. That is to say, you give it a huge amount of data, tell it what your desired false positive rate is, and it will tell you what a reasonable cutoff is. But in order to do that, you need to provide it with enough data. And as it turns out, the APT, because of its window size, you end up needing to feed it quite a lot more data as a result. And so you're looking at something like a factor of 10 times the window size divided by alpha. And remember, alpha is like 2 to the negative 20 to 2 to the negative 40. That means you're multiplying essentially 10W by 2 to the 20 to the 2 to the 40. So eventually that becomes real, that becomes a real amount of data. And so it's a little bit hard to empirically estimate these cutoffs if you're targeting something on the order of a false positive rate of 2 to the negative 40. But at 2 to the negative 20, it actually is genuinely still possible. Okay, so in summary, we've more or less already talked about this. Turns out that the procedures included in 90B give you lower statistical power than it could be otherwise. If you want to choose, you're allowed to choose better cutoffs using other approaches, and you should consider modifying the window size if it makes a lot of sense for your design. And it's easy to just play around using the APT tool to figure out what the impact of the window size here. And then you can use tools from Theseus in order to do this. Okay, so quick meta summary here. It's fairly easy to do better with the APT and RCT by just choosing different cutoffs. You're allowed to do better, so let's do better. Yeah, that's it. Here are the references that I sort of refer to over the course of this. Once these get published, you'll be able to actually refer to these. Are there any questions?
Questions?
I can continue like speed screaming into the microphone for the next 3 minutes if anybody would like that.
Well,
all right, thank you very much.
thank you very much, Josh. The speaker is Yvonne Cliff. She comes all the way from Australia, so thank you very much for coming all this way to talk to us. Much appreciated. She's from Teron Labs, down under. She's the lady responsible for all of the ESV submissions, and she's proud to have at least 10 under her belt. So, yes. Welcome.
Thank you. So welcome to Health Testing with Sample Variance. So this talk is in 2 parts. The first part, we will look at a sample variance health test. We'll have a look at a case study, and is that better? Hello. So we'll look at a case study for the sample variance test. We will compare it with the adaptive proportion test and have a quick look at 2-tier testing. And then the second part of this presentation is a new generic second-tier test improvement. We'll have a look at why it works, and we'll apply it to the adaptive proportion test from the case study and see how it improves that. So why would you want to do health testing with sample variance? Sometimes, for some distributions, the min entropy level is proportional to the log of the sample variance. So in this case, if you work out the sample variance, you can then use that to predict the min entropy of your data. And so you can see on the graph there, I have the straight line for the normally distributed raw data and also uniformly distributed raw data. And so in these cases, this test would work quite well. You can see up the top in the middle, I have some spiky distributions, which I'll show on the next slide. And you can see that they don't lie on the line. So if your entropy source fails in such a way that the data is now coming from a spiky distribution instead of a normal or a uniform distribution, unfortunately the sample variance test is not going to work particularly well in those cases. But if the data always remains normally distributed, a drop in entropy also means a drop in sample variance. There are noise sources around that do produce normally distributed data. So for instance, data from quantum sources, and there's a reference there, and also the number of events in a fixed time interval. There's another reference there as well. So here's our spiky distributions. I just did these for an entropy level of 4. So you can see one spike in the middle on the left, 2 spikes sort of separated from each other, 16 spikes, which is the maximum you could have with an entropy level of 4. And on the bottom at the middle, 1 spike shifted right to one end. And you can see all of these have a sample variance of 5,000 or 6,000. And then just for reference, the ones with the sample variance written in green are the uniform distribution. On the right, an entropy level of 8. And you can see that that variance is about the same as the ones written in red, even though their entropy level is half. And on the left, the uniform distribution with an entropy level of 4 has a sample variance of only 21. So if we wanted this test to work, we would want all those numbers in red to be about 21 instead of 5,000 or 6,000. So just a quick run through of what sample variance is. We let DI be the digitised raw data samples. We choose a false positive rate. We choose a window size. We work out sample variance. I've just got the formula there. You can find it in any statistics textbook. But basically, you have to sum up your data samples. You sum the square of your data samples. You do a bit of multiplication, subtraction, and division at the end of your window, and then you get a sample variance value for each window of data. To calculate a cutoff, you ideally need to know the distribution of the sample variance, and that varies depending on what distribution your raw data comes from. So if your raw data is normal, the sample variance can be scaled to the chi-squared distribution. That was easy to find in my statistics textbook. The others I couldn't find, so I did some simulations. And when the raw data was binomial, the sample variance appeared to be distributed according to the gamma distribution. When the raw data was uniform, sample variance was normal. And this talk was originally 1 hour long, and so I have cut out half the slides and put them as bonus material. So when these are up on the web, if you'd like more information, it's in the bonus slides at the end. So now we go on to the case study description. So we're going to have a quantum noise source, and it will produce data. We're going to assume that the entropy of this data is above 6.5 bits per byte. So this is represented by the purple curve here. You can just see. And unfortunately, we can't measure this noise source directly. When we measure it, it gets contaminated with noise from other sources. This noise is also normally distributed, and it's this aqua colour here. It has a much smaller variance, and the entropy contributed from this data, we're going to assume for this example, is 5. And then the measured data that we can actually look at and process is the sum of the data from the quantum source plus the noise that gets introduced when we measure it. And it turns out that that is this blue distribution that's quite close to the purple one. And it also turns out that because this blue distribution is a sum of 2 normal distributions, the variance of the blue one, the measured data, is the sum of the variance of the other 2. So I have a little graph here. So we've got the min entropy of the quantum data along the x-axis at the bottom here, and the min entropy of the measured data up the y-axis. And then I've just picked a few different values for the entropy level of the noise or the errors, E for error. and depending on how much entropy is in the errors depends on which curve you get. So we're going to be looking at the green curve, which is the case when the entropy in the errors is 5. Now, if you're making a claim that you have a quantum noise source and it's producing some entropy, then your health testing requirements will apply to the quantum noise sources. They won't apply to the measured data. So we can't perform a repetition count test or an adaptive proportion test on the quantum data itself. All we can do is apply tests on the measured data. So then we have to make an argument that if there is a drop in the quantum entropy, that will also cause a drop in the measured entropy, and we'll be able to detect it. So just for this example, I picked a false positive rate of 10 to the minus 20 when the quantum entropy is 6.5. And I wanted to detect a drop in entropy down to a quantum entropy of 6. So I want my health testing to fail at that point. And I also wanted it to fail 99% of the time if the entropy was that low. So I did the math, worked out how often it would fail for some tests. So the sample variance test, it turns out if you have a window size of 313 symbols, it will detect this as we wanted 99% of the time. Comparing that to the adaptive proportion test, with a window size of 512, it fails with a probability of 10 to the minus 18, which for all intents and purposes is pretty much 0. So it's pretty hopeless at detecting this. Of course, if you increase the window size, its detection rate will get better. So I kept increasing the window size, trying to get up to 99%. And when I got to a window size of 2 million, I gave up. That was failing 55% of the time. I said, well, that was a bit hopeless for APT. What if we lower the bar? And instead of trying to detect a quantum entropy drop from 6.5 down to 6, what if we try and detect a drop from an quantum entropy level of 6.5 down to 4 instead? So I've got different window sizes and failure rates for the APT there. So a window size of 512 fails around 3% of the time. If you want it to fail around 50% of the time, you're looking at a window size around 3,000. If you move up to a window size of 100,000, you can get it up to 80%. And going up to 2 million didn't give you much improvement, it was 83%. So when your health test is perhaps not performing as well as you would like it to, as the APT was in that instance, you can move to two-tier testing. So two-tier testing was described in the CMUF working group by a DJ, David Johnson, and it has 2 stages of testing. So the first stage can apply to any health test. For example, the APT, RCT, SVT, just pick one. You can have a high false positive rate on good data, so for example, 1%. And you can have a low false negative rate. That means a high detection rate. If your data is bad, it's got a low entropy level. And this would be classified as an intermittent failure, and data that fails this first tier of health testing would not be credited with any entropy, but it would still be input into the conditioner so that it doesn't change the data distribution. So if you had data failing this first stage of testing, you would just collect extra data to go into the conditioner before you decided you had enough. Then stage 2 looks at the rate of failures from stage 1. So for example, if 50% of the last 256 tests fail, you might declare that as a persistent failure, and you can have a very low false positive rate in this second stage. So the scenarios where you would find this 2-tier type of testing helpful would be when the NIST recommended false positive rates are too high for your application, that is, they fail too often, or the detection rate for bad data is too low, or another way of saying that is the false negative rate is too high. If you have a fixed length conditioner, it becomes a little more complicated because you can't credit or not credit data with entropy. Everything, because the conditioner has a fixed length, everything is credited with entropy. So in that case, you would have to buffer the output of your conditioner until the second tier of testing had passed for that data, and then you could release it. So here's my table of numbers comparing the SVT and the APT. So I did 2 versions of the SVT. The first one is the one we already looked at with a window size of 313. And the second one, just for fun, I picked a smaller window size to see what would happen with 2-tier testing. It becomes a bit more inefficient just because you're using a smaller window size and then you have to do the 2-tier test. And then I have 5 different APTs there. The first one, I was trying to get the detection rate on the first level test up to 99%. I couldn't quite manage it, but we got up to 97%. Unfortunately, that means it also rejects nearly all of the good data as well as nearly all of the bad data. So it rejects 92% of the good data, which makes it very inefficient. The second one has a nice separation in between the detection rate and the false positive rate. You can see it detects 70% of the bad data, but it only rejects 7% of the good data. This third one here, the cutoff is chosen according to what's recommended in the 90B standard. So for a false positive rate of 2 to the minus 20, and you can see it's, like I said before on the other slide, it only detects 3% of bad data when the entropy level of the quantum data is 4. I also tried the APT with a smaller window size, so I picked 64 for the smaller window, and I just tried to get a couple of tests with a good separation between the detection rate and the false positive rate. So here we've got 67 versus 36% and 35% versus 8%. I've got the number of second level windows and cutoff there, but these were all chosen such that I got the second level false positive rate as close to 2 to the minus 20 as I could, with a second level detection rate of 99%, just so that we can compare these trying to achieve the same thing. The exception is the NIST test, which is the second level false positive rate of 2 to the minus 12. So the 2 to the minus 20 is at the first tier instead. So the number of symbols we needed to produce a 256-bit output block with full entropy, you can see the SVT wins at only 54 symbols, and the others have 80, 100, or the really hopeless test, 1,000 symbols to produce the same amount of entropy output. Another thing that I think is really important is how much bad output is there before these health tests detect that there is a problem. So this is the average amount of bytes or kilobytes output per second tier test. So you can see the SVT tests are only putting out, on average, 2 or 3 bytes per test. So this means most of the time they output nothing, and then once in a while they output an entire block of bad data, and it averages out to 2 or 3 bytes per test. The others, the APTs, are all outputting kilobytes of data, and in particular the NIST test, or if you choose it with NIST's recommended parameters, it's outputting 30 kilobytes of data before it detects that there's a problem. The bottom row here is if you've got a fixed input length conditioner, how much data would you need to buffer before you could release it? And again, you're buffering very little data for the SVT and much more for the adaptive proportion test. So this is looking at a similar thing in a little bit different way. So across the bottom, we have detection rates. So if you have bad data with an entropy rate of 4, what percentage of the time will the test detect this? And then up the y-axis, we have how many thousand samples. So you can see how many thousand samples do we need to detect bad data a particular percentage of the time. So these are both the same graph. The one on the right is just zoomed in to the bottom of the one on the left. So the red one is that hopeless APT that rejected nearly everything, good or bad. The purple one is the APT chosen according to NIST's parameters. So it's second worst. The solid line here in sort of blue or aqua is the other 512 window size APT. It's doing a lot better. The dotted lines are the 64 window size APTs. So you remember there was 2 of those. And so we can say detect 50% of samples, sorry, 50% of the time we can detect that the data is bad with about 7,000 samples in the top one there, or about 5,000 samples in the bottom one. And then the lowest 2 here, the best performing, are the 2 SVTs, the SVT with a window size of 313 and 64. So I hope this convinces you that sample variance health testing is well worthwhile if you have data that's conducive to using it. So part 2 is the new generic second tier improvement. So this applies to any tier 1 test that calculates a test statistic. So for instance, the adaptive proportion test calculates a count. It counts how many times the first sample appears in a window. The repetition count test generates a count of how many values were the same in a row. The sample variance produces a sample variance. And this also works for pass or fail. So pass or fail is what we saw before. That's a special case of this generic improvement. So for the second tier, before we counted passes or fails, whereas in this improvement we're going to take an average of the tier 1 test statistic, and then we'll compare that average to a cutoff to then generate a tier 2 pass or fail. So I looked at 2 different types of averages, a simple moving average and an exponential moving average. Both of them you need to choose a window size and a cutoff. For the simple moving average, you have to keep a list of the last W tier 1 test statistics. You can initialize the list with the expected value of the test statistic for good data. And after every tier 1 test, you update your window, you overwrite one of the old values with the new value, and you take the average of all the values again, and you compare it with the cutoff. The exponential moving average, you also choose a smoothing factor, and you calculate this multiplier using the smoothing factor and the window size. And then you calculate the exponential moving average. It is the test statistics times the multiplier, plus your previous exponential moving average times 1 minus the multiplier. And then the same as before, if this new exponential moving average that you calculate is above or below your cutoff, depending on your situation, then the test will fail. So why does this work? It's because of the central limit theorem, which says that if you average n samples, you reduce the variance by a factor of 1 over n. So this example here is for the adaptive proportion test with a window size of 64, and I took a simple moving average over 60 values out of the APT. The green line here represents the distribution of the APT counts on good data where the quantum entropy was 6.5, and the maximum value, so that I found these using simulation, and the maximum I got when I was simulating this was around 7 or 8, which is actually off the graph. The red line represents the distribution of the APT counts for bad data when the quantum entropy was 4, and the maximum value for that count was around 10 to 12, which is also off the graph. But then when you take so you can see that trying to tell the difference between the green and the red is not easy, especially when for the count to be from the red distribution, you know, it has to be off that graph. It happens rarely. But if you take the average, the green turns into the blue here, and the red turns into the gold. And you can put a cutoff here at the purple line at 1.9, and it is far easier and quicker to tell the difference between the good data and the bad data. So on average, I only needed 35 values coming out of the adaptive proportion test before it moved that average past the cutoff. So even though the window size was 60, I didn't even need 60 sample variances from bad data, only 35 on average to get it past the cutoff. And the maximum in my simulation was about 129 values from the APT test. So this is the same type of graph as before. So I have one side is for the APT with a window size of 512, and the other side is for APT with a window size of 64. And I've kept the same scale on both of them so that you can compare them. So the purple one is NIST's test again. The gold one is the best out of the APTs that I looked at. And then the blue and the aqua lines down the bottom are where we use the simple moving average and the exponential moving average. And you can see there's not a lot to choose between them. They do tend to cross over here on the right-hand side of the graph. And again, the 64 symbol window APT performs better than the 512. And so basically this graph is saying if you use some sort of average, you can detect the same failure, the same percentage of the time with half the amount of data, because these lines are at about half the height of the other ones. So just to finish off a few things that I didn't really have time to go into in detail in this talk, but I wanted to bring to your attention in case you're implementing this. If your distribution has significant tails that end up in the first and last bins when you digitise this data, this is going to affect the sample variance. It will make the sample variance lower because in the undigitised distribution, these tails would have sort of gone out the sides here and been a lot further from the mean, and that would have increased the sample variance. So when that happens, it means that good data is less likely to pass the health test. It may or may not be a problem, but if it is, you may need to modify the test a little bit just to take it into account. Skewed data has a larger variance than unskewed data. So in the bonus slides, there is an algorithm to sort of do a circular shift of the data to shift these right-hand values round to the left and get this spike in the middle so that then your variance is lower, so that then the sample variance test has a better chance of detecting a drop in entropy. And a quick note about two-tier testing for sample variance. It's probably not particularly beneficial to do a second tier with the sample variance test because you can get just as good a result using one big window using the same amount of data as what you use for the two tiers. So there's some variance calculations that show the point if you're into math. So in conclusion, the sample variance test can be far more efficient than other tests like APT if your data is conducive to this type of testing. It needs less data. It has a higher probability of detecting low entropy data. It detects a much smaller drop in entropy, and it will result in a higher throughput because you're crediting more data with entropy. Unfortunately, it might not work if the bad data distribution has significant spikes. And for the improvement to the two-tier test using the simple moving average or the exponential moving average, this is more efficient than just using the pass or fail version. The simple moving average and the exponential moving average give similar results. If you use the simple moving average, you do need to keep a list of prior test statistics. So if you have a shortage of memory, that could be a problem, but the exponential moving average doesn't. To find the best window size, you just have to use trial and error, try them out, see how they perform using some simulation. And to find the cutoffs, you could do that using simulation, or you could use some simulation to estimate a statistical distribution and then use the statistical distribution to then work out your cutoffs. So thank you very much. That concludes my talk.
So we have literally a minute for one question. Are there any questions for Yvonne? Josh.
So you mentioned that using the second tier testing wasn't very helpful for the variance-based approach that you looked at. Did you compare the effect of what happens when you just let your APT window grow to the sort of morally same size as the second tier testing? And I guess the interesting follow-up on that would be what is sort of optimal? What choice of window size is best if you're doing this second tier testing so that you pick up on these things most efficiently?
I didn't do a direct comparison, but we could probably find something here. Say we're using 3,000 symbols to get a failure rate of around 50% there. Now you need your mental math to see which of these two-tier tests uses 3,000 symbols. Might have to look at it offline. My mental math is not quite that good.
Well, thank you very much, Yvonne. Much appreciated.
Can everybody hear me? Yeah? Okay. So I'm sorry for the slight inconvenience beforehand. I have hopefully a lively Q&A. Mine's a lot less technical of a talk. Mine is much more general for everybody who may not know about ESV or who's ESV adjacent. I'm not introducing you to the program. I'm more telling you what the PUDs have shown, what's been certified, what labs do what. It's a very general topic. I feel like it's of interest to everybody. It is to me, so just small disclaimer, everything here is not, it's publicly available, and they're my opinions of, so if I say like, this is an interesting report, it's my opinion. But I've read all of the PUDs up to this point. In fact, I was in the back finishing up a few because they had one that came out the 16th. So had to update my report to include that. But when you start reading these and you're trying to get information from like the ESV site, you're given this lovely cert, and this is just for the very first one. And here you have a little bit of information. You see the operating environments. In this case, you see that there's a conditioning component. You know what lab did it, when it was done. But that information that most people care about, like what's happening underneath, well, unfortunately, that's hidden from everybody. That's in the EAR, but a glimpse of it's available in that link at the public use document. So when we click it, we're given a document, short. The intent of the document is, I feel like, to model what a security policy would model with a module, just some basics about how it operates, what to expect, how to communicate with it. And reading this gives you a lot more information than the others. So I've collated a lot of the results, and we can look at some general stats. So up to date, there have been 190 ESV certs awarded. There are 663 OEs that have been certified across the ESV certs, and that number can be further subdivided because some of those apply to a product family, and we'll look into that, thinking of Intel there. There are 17 labs that have ESV certs awarded, and there are 81 vendors with different certs. So the question is, who's doing what? I think we all know right now ATSEC has done the most in terms of the number of certs awarded, followed by UL and Leidos, and you're seeing a lot of the other labs come up. I wish I had a timeline because you can see kind of other labs starting a little bit late but really growing momentum in how much they're submitting. But this is only part of the question. Let's bring in the OEs a little bit. So how many OEs have each lab covered? All right. So some labs have covered quite a few, and these certificates generally have a little bit more complexity. You have some more data to look at, and it's something to consider when you're picking a lab, is kind of that density there. But something else to consider is what constructs are being used. I think to the people working in this field, this is the more interesting part. So I was actually surprised when I finished and got the numbers here. I was expecting Gent to just beat out even ring oscillator constructs, but that's not the case. Gent will probably beat it pretty soon, though. The question mark is you can't determine from the noise source description in the PUD or the cert. There's not enough information provided. It could be physical. There are non-physical noise sources as well that aren't described how they get the information, which might be a problem if you're looking at using the PUD for something like CC in the future. If you have an ESV cert, but the evaluator can't figure out how the noise source is even operating, the PUD's not enough information on its own. So it's something to consider. But then we also see a lot of Intel DRNG. And then there's some non-gent, those are like software interrupts. There's some cool quantum noise sources, and we'll talk about those later. And then a few oddballs, the chaotic map, NAND jitter for like NAND flash. One of the coolest ones I've seen, which is device motion, and I wish I could have that EAR. They're using an accelerometer in your device to get Entropy, which makes sense, but it's the only one that's done, so that I want to see what they did. So if you have that EAR, my email's at the end of the slideshow. And this data, I can make it available. I know it's kind of small, but I think what is also quite interesting is what lab does what. There are some labs that do more gent work. There are some labs that do a very wide variety of topics. If you're noise source, if you haven't seen it done before, find a lab that's used to doing a lot of different ones. They might have a different strategy. If you have a quantum noise source in particular, look at the ones who've done quantum. If you have gent, a lot of labs have done gent. ATSEC really has gent down too. So visit one of the labs that have done gent. But even if they haven't, the Entropy Working Group, people are starting to build in their gent repertoire and submit gent, and there's a pretty nice process for that now. And of note, there are also some labs that have done just one, and those are, most of them are very, they're also the lab that did a module submission for one vendor overseas usually. I'm thinking of like SSD manufacturers that happens. But yeah, let's talk about just gent for a second. Who does gent? So ATSEC does gent. But also you're seeing Lightship do quite a few of them. And the number of OEs is definitely something to consider when doing this. Most gent certificates are awarded for a large range of products because, as we know, gent is pretty portable and you can implement it in a lot of places. But ring oscillators are also, there are many different constructs, and after my presentation section in the Q&A, I can tell you what those different constructs are. There are many different ways to put these ring oscillators together. There are also, actually, I think that's the best way to say it. There are many ways to put these ring oscillators together to get what you're looking for, and there's a few common designs that come through. You see a lot of, Broadcom in particular has a cert that you see the PUD reproduced multiple times across different certs because they've updated their design, changed their manufacturing process. Unfortunately, a lot of those are closed for reuse, so you have to talk to them to use it, but it's clear that they're trying to provide a hardware noise source to vendors. And then there's read RAND, read seed. So here is interesting, right? You see Teron Labs, Leidos has done quite a few of them. We've done 2 recently, Decra's done 1. And this information, the sum of the number of OEs, hides a lot. Because when we think of an OE, we usually think of a very specific platform, but read RAND is a custom silicon part. It's not like ring oscillators where the layout changes every time you get a new die. So this is just E64. And in this one, if you look at the number of operating environments, there's 1 listed. But you go to the PUD, and there's 20 different SKUs there. So overall, there are 570 different SKUs across all of the certificates of Intel Read RAND, Read Seed that have been certified so far. And I say at least because to do this was a very manual process. I went through and counted on each of them, and if I missed one, that's quite possible. So at least 570 Intel SKUs have been distributed across these certs. But something else to note here is, of those, if we go back, the one by Decra and one of the ones we've done, they're not restricted to vendor, they are actually Intel's. They belong to Intel's. Notice the vendor here is Palo Alto Networks. So this was done within, probably for their module submission. And the constraints there, I think Simon pointed out the distribution network and kind of talking about multi-tenant devices, you have to consider when you're doing an entropy source validation for just read RAND, read seed, what can other things do? And you have to really question that quite a bit. And it makes for a lot of fun conversations with the CMVP and getting them used to the idea and asking their input. So yeah, let's jump back one. So these are the 2 certificates I was talking about with DECRA and EWA Canada. They're both open for reuse. And within them, you'll see either for this processor family or this set of SKUs. This is something fun to consider, and hopefully there will be many more. But I got into this because I like the unique designs. Gent is a really cool construct, but doing Gent certs all day can get a little, it pays the bills. But these are the really interesting ones. And something to note here is that electronic noise, I really wish I had another label for it, but it's quite literally volume noise, like acoustic noise in the device. So that's a pretty nifty noise source that, once again, if you have the EAR, my email's at the end, and I'm very interested. But here you can see the cert number as well. I added those. So each one of those, you can go look it up, read the PUD, it's fun. And then which labs have worked on these unique certs? So they're unique, they're not handed out often. We're very honored when we get the joy of working on one, and we hope to work on many more, and I think every lab does. You get to learn a lot and speak to some very smart people in the process. And then one of a lot of interest to me back there, and EWA Canada did it before I started working with them, but this is the only IID noise source so far that has been certified. So it's one of the quantum noise sources, and the PUD, I put a picture there. I should be able to scroll. Well, I can't. It's literally a picture, but you should go look at it. It's a very detailed PUD. So it explains a lot about the entropy source, and it's one of the most explanatory. Now, this is towards the end of my talk, but one thing I do want to bring up is on that cert, that entropy per sample is a source of stress because it's not the entropy per entropy source sample, it's the entropy per noise source sample. And the person consuming this entropy certificate usually doesn't know that by default. They're a person working on a module, not on the entropy source itself, and then they look at this and make an assumption about the behavior of the entropy source. But usually, luckily, that's the worst case scenario. So if you seed your DRBG under that constraint, it's usually safe. But often the entropy rate is a lot better. So in this one, I also brought it up because it's interesting. You have a choice of using the conditioning component or not in that entropy source. But here, when you're using the vetted conditioning component, you're getting full entropy. So looking at the cert, it doesn't tell you that anywhere. And in fact, having a vetted conditioning component doesn't mean you'll get full entropy. So you have to actually dig in the PUD to figure out the performance characteristics of your entropy source. And I have 2 honorable mentions that I really like a lot. One is E21, and E21 is very interesting to me because look at those last 2 operating environments. So you're seeing Raspberry Pi Model 4s getting entropy source validation certificates. But not only that, in the PUD, it's the default Raspbian OS. So it's not a proprietary OS, default Raspbian, and you're getting access on the dev random on that machine to an ESV certified entropy source. And then, yeah, I just have to keep coming back to this one, this E86. I need to find that EAR. I will one day. And this is the accelerometer-based entropy source. I'm going to end up just buying the product just to play with it. But I'll go back. I saw a camera rise and we're taking an image. But yes, this is the time to Q&A because I actually have my Excel spreadsheet with all of my notes, and it's rather lengthy. So if you have a question like, what are the different type of ROs? That's a pretty basic one. But also, what are some odd things you've seen? What notes have you had? Feel free to ask them now, or if you're joining the Entropy Working Group for, I guess, the bar crawl, then of course ask me there too. But thank you. Oh yeah, I let everybody go early. I know I'm the last one. It's 5 o'clock. Well, it's 7 o'clock for me. Nothing. Let's see. I'll just bring up the spreadsheet to show you. I'm not really kidding. I went through and there's the information that you can get off of the cert, but then there's a bunch of properties like what are the ring oscillators doing and how are they combined? What does that entropy rate out?
Yes, it's very impressive to have gone through every single PUD. I don't envy you for doing this. At the same time, I don't think we could, Tim and I could offer a classification like this because I think we would be too biased having read all the EARs.
I'm jealous.
Well.
I don't have to give feedback. I just read and I can make my snarky comments in the corner and nobody knows. So.
I mean, maybe we do that, maybe we don't too. I guess one interesting one, I believe, is E174, if you have it in your spreadsheet.
Mm-hmm. Scroll. Okay, so that's going to be 174 is Red Hat kernel CPU jitter?
No, I'm sorry, that's not the number.
I was concerned.
Maybe
you found
80?
the gent one interesting. Love your job.
I like that 181.
181.
Yeah.
Okay.
Did you look at the OE for this?
This was this the
Yeah.
VR display? Yeah. I think I actually made a note. Yeah, so this one.
Oh, yeah, that's fun too, but that's a different thing.
So yeah, that was interesting because it's like, okay, well now your Vision Pro or the.
For context, this is the Apple Vision Pro that came through our door, which I get really excited to see stuff like this, and of course I can't talk about it until after we publish the certificate. But an interesting one, a double use of SHOT 512 on the conditioning chained into each other. It's allowed. It's valid. It's approved. But yeah, this list is neat, and I might actually ask for this for our own, record keeping.
Yeah, CC Simon, I need his permission.
Yeah. So thank you for this.
Cool. Well, feel free to ask me in private as well if you're just curious about what lab does what and you don't want to ask everybody else or let everybody else know. I got it. Okay. Well, thank you. I'll let you guys go early.